let's spend some time talking about organic chemistry. Just a little bit of an overview, just to kind of get you exposed to it before you actually move out of that course. So, first up, what is organic chemistry and why do we care? Why is it so unique? Organic chemistry is really the study of chemistry or of carbon chemistry and its friends. So, it's study of carbon and the elements that want to hang out with it. You're going to see a lot of hydrogen. You'll see a lot of oxygen, nitrogen, sometimes some of the halogens, maybe some phosphorus, some sulfur, but it's really carbon and its friends. Carbon chemistry is unique because, well, two things listed here tell you. First, the number of compounds that contain carbon is greater than the number of compounds containing all other elements combined. What do I mean by that? I mean if I took every single compound in the entire world, everything we have, and in one pile, I put everything that contains a carbon atom. In the other pile, I put anything not containing a carbon atom. The pile with carbon is bigger. Carbon's in everything that is living or has ever lived, plus other things. But it's very, very abundant on Earth. It's also the reason that the entire periodic table is based on carbon-12 specifically. Carbon's unique behavior includes its ability to form covalent bonds. It really likes to form covalent bonds. Other elements do too, but it really likes forming covalent bonds. It really likes forming double and triple bonds, and not all elements like doing that. There's actually just a small handful of elements that want to form the double and triple bonds. Carbon also forms chains, and so it does this by covalently bonding to itself multiple carbon atoms in a line or in a chain or a branched compound, meaning a chain with other carbons coming off of some of the carbons. It can create very complex structures of carbons bonding to one another. And most elements don't bond themselves very well. So here's just some different organic molecules that you might have had or been exposed to in your everyday life. First up, lifesavers. We've got what we in the grocery store would call oil of wintergreen. The common name would be methyl salicylate, easier to remember for people that are using it regularly. And its actual name is methyl 2-hydroxybenzoate. So we have what we call your chemical name, your common name, and then your really common name. But this is the compound that gives that wintergreen smell and taste in lifesavers. The lifesavers hard candies. We have ethanol. Ethanol is also known as grain alcohol. I often write it as ETOH because it's just faster. It's also known as ethyl alcohol. And its compound is here. Ethanol is what people drink. It's the alcohol humans consume. We also have octane and isooctane shown on here. And notice I've got these structures drawn a little bit different as well. So first, we're going to talk about this in just a minute. But backing up a little bit to the oil of wintergreen or the methyl 2-hydroxybenzoate compound, every time I see a corner change, this is where a carbon atom is. And each carbon atom has enough hydrogens on it to give it a zero formal charge. So we're not drawing out the carbons or the hydrogens, we're only drawing out hydrogens if they are attached to an oxygen on the other side or a nitrogen or some other compound on the other side. But it's a quicker way for us to draw the compounds. It's called what I call the skeletal structure. For ethanol, you see it's not a space filling, but it's a ball and stick method. So we got our carbon atoms, our oxygen, our hydrogens. So in this one, everything's actually shown out. But again, this is called your ball and stick method. It's showing all the structures. The last two we have here, octane and isooctane. The structure here is called your space filling model. And they look really cool. They actually show you how the molecules are put together. They show you how much space each thing takes. You do need a computer model to be able to do them proficiently and properly, but they actually take in the size of the atoms, of the atoms radii and all those kind of things to make the models. But I have octane and isooctane shown here because these actually have the same chemical formula. If I was to count these up, I would find it to all have C8H18 for its overall formula. The difference is octane is what people think of when they think of gasoline. They think of an octane rating. Isooctane, which is its common name, it's also known as 2,2,4-trimethylpentane, is what's actually determining that octane rating in your gasoline. Just another organic compound. So I know we got exposed to this in the previous slide, but let's talk about it a little bit here. The different types of chemical formulas. You guys are used to expanded or maybe condensed formulas. You guys are really used to just writing out the formula itself, and then if I actually ask you to put it together, your expanded formula is like your Lewis. Okay, that's your Lewis structures, and then condensed formula is just kind of, again, condensing it down. So you can see the first structure, you condense down our CH3 and our CH3. Or you can write them, here and here as well. We've condensed down your OH. And then we've condensed this H onto the carbon here. We have your fully condensed formula. And again, fully condensed is by the way we've drawn them, we know where the carbon atoms are. So anytime we have the end of a line, we're a carbon atom. And anytime the line changes direction, we are a carbon atom. End of the line, if you have an element listed though, that is the element, not a carbon. But then I know that those carbons need to have enough hydrogens around them to give them a zero formal charge. Carbon always has 4 bonds. That can be a triple and 1 triple bond and 1 single bond, 2 double bonds, a double and 2 single, or 4 single bonds. But carbon needs 4 bonds. So this carbon here only has 1 bond, so we know that it has 3 hydrogens to give it its 4 bonds. Same thing with the carbon here. It has to have 3 hydrogens to give that carbon its 4 bonds. And the one in the center has to have 1 hydrogen to give that carbon its 1 bond. It's called a fully condensed formula. I just call it your skeletal structure. The carbons and hydrogens are missing, but they're understood and implied. And then again, your space filling model. Space filling actually incorporates in your Vesper angles and your relative atomic radii and your bond length. So it gives you a true idea of what the structure actually looks like and size comparison. So your condensed formulas. I won't draw them very often. Once I teach organic, I really just like to draw skeletal structures. It's faster. But you will see condensed structures in condensed formulas, and you should be able to be comfortable with them. Remember, on your condensed formula, your proper bond angles are not shown here. The hydrogen atoms will be drawn next to the carbon to which they are attached. So the hydrogens here are attached to this carbon. Hydrogens here attached to this carbon. How do I know they go to the one before it and not the one after? Because every carbon atom has to have 4 bonds. And so I've got the first thing listed here as a carbon. That means whatever's after it has to be attached to it to give it the 4 bonds. This hydrogen goes to this carbon. Why do I know? Well, again, I've used up the other hydrogens, but 2, I've got a double bond right here. The double bond has to be between the 2 carbon atoms. I apologize. There's a kitten in my house, or 2 of them, and they were quiet until I decided to make the video. But I don't have the care to stop her. So these 2 carbon atoms are double bonded. There's a hydrogen here. Oh, wrong button. This CH3 group is attached to this carbon, and this CH3 group is attached to this carbon as well. You can see them written here as well. The hydrogens here on the carbons. And then the hydrogen onto the oxygen here. So single bonds are generally not shown, but they can be. We see that we do have a single bond shown here. Okay, and that's partly because it's a branched compound. It's coming off of the main chain, your parent chain, as we're going to call it. This is your main chain. This is your main chain. Okay, so it's got a branched compound coming off there. And so we will often show it when it's got something coming off like that. Lone pairs are not specified, but you should know that they're there, and you should be able to tell me anytime I ask you to put where lone pairs are. Lone pairs are always implied, but we don't usually draw them in anymore. Okay, so our skeletal diagrams. Imagine the locations of lone pairs and hydrogen atoms. Remember, carbon and hydrogens are not emphasized. We don't actually write out the carbon and hydrogen. We will write out hydrogens if it's attached to something like an oxygen or a nitrogen, but we won't write it if it's attached to a carbon, okay? And so the end of every line is a carbon atom, and anytime the line changes direction, it's a carbon atom. So what is the chemical formula of each molecule? Well, let's count it. First thing I want to do is count the carbons. I know the end of every line is a carbon. So there's 3 carbons. I know every time the line changes direction, it's a carbon. 1, 2, 3, 4, 5, 6, 7, 8. And I've got one listed right here. So C9. Notice this right here is not a carbon because it's got the bromine right there. What this means is that this bromine is attached to the carbon atom down here. Okay? So when I say end of the line, if there's an element listed there, that is not end of the line with a carbon atom right there. This is C9, BRN, but I forgot one element. I can't forget my hydrogens. They are definitely here as well. And I need enough hydrogens to make every carbon have 4 bonds. So this carbon right here already has its 4 bonds. It doesn't need any more. This carbon right here has 3 bonds. It needs 1 hydrogen. This carbon down here only has 1 bond. It needs 3 hydrogens. The carbon here has 2 bonds, so it needs 2 hydrogens. This carbon needs 1 hydrogen. This carbon needs 1 hydrogen. 2 hydrogens. 3 hydrogen. And 3 hydrogens. So let's go ahead and count that up. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Probably won't usually write it like that. We'd probably write this formula more along the lines of like C9, H16, BRN or NBR, one of those two. Usually keep your carbons and hydrogens together, but it's just looking for the formulas. Let's do the next one. Let's cut up our carbons first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Now let's count up our hydrogens. I've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. And the last structure listed. Count up our carbons first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And our hydrogens. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. With an O. I think I counted those right. If I counted it wrong, I don't have notes in front of me, so write down the right formula, but I think I counted those right. I know the carbons are right, but you need to have enough hydrogen. I know the numbers written next to them are right. I just don't know if I added them up right when I was talking. Okay, so isomerism. We've actually seen this idea of isomerism. Let me scroll. I apologize. Back here. This is an example of isomerism. If I actually, now that we've talked about looking at formulas, let's actually add up the formulas of these things. If I look at octane, I've got 1, 2, 3, 4, 5, 6, 7, 8. And then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogens here. If I do something similar for isooctane, 1, 2, 3, 4, 5, 6, 7, and 8. And caught it before I did. Right here. This carbon can't have any hydrogens because it's already got 4 bonds. If I look though, they have the same chemical formula, but they have different connectivity of the atoms. Identical chemical formula though, but they're not the same compound. They have different boiling points, they have different melting points, they have different reactivities, but they have the same formula. That is what is known as an isomer. So isomerism. Structural isomers have the same chemical formula, but different connectivity of the atoms, meaning a different arrangement. They have the same chemical formula, but different. They're overall different molecules. So example, C3H8O has 3 isomers. I could have 2 alcohols and 1 ether. We will talk about functional groups in just a bit. But we see here we've got 1 propanol, 2 propanol, and ethyl methyl ether. If I actually drew the skeletal structures of these, it looks like this. It looks like this. And it looks like this. They all look different, but they all have the exact same chemical formula, C3H8O. So you can see that different amounts of carbon content in the compound will result in a different number of isomers. What this means by carbon content is how many carbon atoms I have in it. what its chemical formula would be if it was just a straight chain, or not straight chain, if it was just a non-cyclic, all single bond molecule, okay? No double bonds, no triple bonds, just all single bonds throughout. It could be a branched compound, which we'll spend some time with, but no double bonds, no triple bonds, no ring structures. 4 carbons, has the molecular formula C4H10, and it has 2 possible isomers. It looks like this, or it looks like this. As I increase, C6H14 has 5 possible isomers. C10H22, 75 possible isomers. C20H42, over 100,000. Those are all different compounds, okay? And so you guys need to be able to look at these different formulas and give me isomers. Draw out the isomers. What is the longest chain? Can you locate branches? Be careful of free rotation. I'll talk about all these things in the video, but I need you thinking about these things because the different isomers are different compounds. So first, free rotation. We've talked about this in Chem 1, but remember, free rotation. If I have a single bond, the molecules can freely rotate along that bond. What that means here is that these freely rotate, freely rotate, freely rotate. These two structures shown here are the same exact molecule. All it did was rotate here at this position. This bond just kind of rotated down a little bit. It's the same molecule though. It just kind of bent itself. The molecules will do that. There's called scissoring, wagging, bending. There's different stretch patterns the molecules undergo to release their own energy. And so single bonds, free rotation. Here are some the structural isomers of C4H10. I remember on the slide just a minute ago, I said there's 2 isomers for C4H10. And I drew one out that looked like this and one out that looked like this. Well, these are where they're at, just drawn a little nicer than what I did. We've got butane, which has a boiling point of 0 degrees C, and we have 2-methylpropane, which has a boiling point of -12. They're the same chemical formula, but they're connected differently. Notice here I've got all 4 carbons in a single chain. Here I've got 3 of the carbons in a chain and then 1 carbon separately from that. The carbon that's separate is called the branched group. It's branched off of the parent chain. The parent chain is the longest chain you have in the structure. So looking at some isomers here, again, the one that we were just talking about, butane and isobutane, which is also known as 2-methylpropane. I've got the 4-carbon chain. That's what these 2 pictures here are showing. Or I can have the 3-carbon chain with the methyl group hanging off of it. We will talk about that, but that's what I'm seeing here. I've got the 3-carbon chain. I've got the methyl group hanging off. And then the space filling has the 3-carbon chain with the methyl group hanging off. Whereas these just had the 3-carbon chain, 4-carbon chain, 4-carbon chain. Notice over here though, on this side of the screen, all of these are actually this first compound. They're all N-butane. N means straight chain. Straight chain. Straight chain. Straight chain. So it's just the same molecule. It's just bending in different ways because of the free rotation around those single bonds. So while these 2 are isomers, these are not because they are the same molecule. Which carbon atom is bonded to only 1 hydrogen atom? Hopefully you guys all say B. A has 3 hydrogens, F has 3 hydrogens, E has 3 hydrogens, D has 2, and C has 2. B only has 1. And of course, if you see some kind of structure like this carbon has 0 hydrogens because it has 4 bonds. This has 3, 3, 2, 3, and 3. We also have cyclic compounds. The major carbon chain involved in the formation of a triangle, square, pentagon, hexagon, heptagon, octagon, etc. They can get bigger and bigger. It works the exact same way. When it changes direction, it represents a carbon atom. So on this structure here, we've got a carbon, a carbon, a carbon, a carbon. Okay? But let's look at what the picture's telling us here. It says that this carbon here, so the one right here on the corner, this bottom left-hand corner, has 3 bonds. It has one single bond. We see the single bond going this direction. And it has 2 double bonds going this direction. Okay? Therefore, one hydrogen atom is attached to that carbon atom that's not shown. And if I look at it, all the carbons look like that. This carbon, a double bond going this way and single bond going this way. So it has one hydrogen atom. Same thing with the one here and the one here. So the overall formula here would be C4H4. Again, each corner represents a carbon atom. The hydrogen atoms are often not shown. They may be shown every so often. We may draw something like this, but most of the time we won't. If I was to draw that structure, I would just do this. A cyclic compound here as well. Notice the carbon here, there's no double bond here, so this carbon on the corner right here actually needs 2 hydrogen atoms bonded to it to get the 4 bonds to that carbon for the 0 formal charge. So which of the following are structural isomers? What does structural isomer mean? It means same chemical formula. But the connectivity of the atoms can be different. What's the easiest way to tell? Well, figure out the formula. 1, 2, 3, 4, 5, 6 carbons. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I've got C6, H14. Here, 1, 2, 3, 4, 5, 6. I've got 6 carbon again. But notice my hydrogens have changed. Each carbon here has 2 bonds, so it only needs 2 hydrogens. So overall, H12. And the last one here, 1, 2, 3, 4, 5, 4, 5, 6. C6, 3, 4, 5, 6, 7, 8, 9, 10. But notice the carbon right here has a double bond this way and a single bond this way. So it actually has 3 bonds. It only needs 1 hydrogen. Same thing for the carbon here. It has a double bond and a single bond already. It only needs 1 hydrogen. So H12, because I was at 10, H12 is the formula. So here, 2 and 3 are my structural isomers. Another type of isomer we have is optical isomers, and these are known as enantiomers. Enantiomers are non-superimposable mirror images, and I highly recommend just playing with a model kit to see this. It's the easiest to do when you have a model kit in front of you, okay? But they're non-superimposable because they have a chiral center. Chiral means that I have an sp3 hybridized carbon, which means it has 4 single bonds. And each group attached is different. So notice on the carbon atom here, I have a hydrogen, a methyl group, a bromine, and a chlorine. It has 4 different things attached. It has a mirror image, ClBr, CH3, and H. It looks the same. They are identical. They are not identical. They appear identical. The chlorine, the bromine, the methyl group on the outside, and the hydrogen here. But these compounds cannot be rotated to have the exact same connectivity as what we have here. And it's hard to see down here, and that's why I say use a model kit. But if I let's look at this one here, okay? If I try to rotate this to match this one, I need the chlorine on this side. If I rotate it to the chlorine is over here, that's going to put the CH3 group right here and the bromine right here. Now my bromine's out of whack. My bromine was fine to start with, though. If I rotate this to get the CH3 group right here, it's going to put my chlorine here, my bromine here. No matter what I do, I cannot get it to this structure. And again, it's hard to see unless you play with a model kit. So I recommend borrowing a model kit and playing with it. But why are these important? The mirror image cannot be rotated to make all of its atoms align with the same atoms in the original molecule. This is important because this is an optical isomer. This tells me that this carbon in the center here, both molecules, is what we call a chiral center. Enantiomers have 4 different groups attached to that tetrahedral sp3 carbon center. Why do I care? Because these two molecules have the same physical and chemical properties, but they're going to interact differently with other chiral molecules. This includes enzymes. So if I mix this compound up with another chiral molecule, it's going to behave differently depending on which molecule which chiral center it's interacting with. And you're going to learn how to name these in organic chemistry. But including enzymes is really important because in the drug world, we have things called like D and L. So like you can buy I have a friend that takes lysine for skin and nails, and she buys L-lysine. You can't buy D-lysine on the counter, over the counter. You can buy L-lysine because L-lysine is what is beneficial for skin and hair. Well, it's because the L is the one that's interacting properly with your body, not the D. And some of them, I don't know about lysine specifically, but some of them, the form that does not interact well with your body can actually cause serious side effects. So, of course, we know that those aren't just sold over the counter for people to consume, thankfully, but still, they will react different ways with different other chiral molecules or with other enzymes, which can also be chiral. So if it's a chiral molecule, including chiral enzyme, it will behave a certain way. So can you recognize a chiral molecule? A chiral molecule is a molecule that has 4 different groups attached to an sp3 carbon, even if the atoms that are bonded directly to the carbon are the same. So let's talk through this molecule and see why it's only carbon 3 here. Notice they're numbered 1, 2, 3, 4, 5, 6. It's only carbon 3 here that's actually chiral. When I look at carbon 1, I've got 3 hydrogens attached. Can't do it. Can't have 2 of the same group attached. When I look at carbon 2, I have 2 hydrogens attached. Can't do it. Can't have the same groups attached. Okay? I see the same thing for groups 4, 5, and 6. 4 and 5 each have 2 hydrogens attached. Group 6 has 3 hydrogens attached. Can't do it. But group 3, or carbon 3, I keep saying group, I apologize. Carbon 3 is a chiral center. If I look at this compound right here, it has 4 different things attached to it. It has a single hydrogen. It has a CH3 group, which we call a methyl group. It has a CH2CH3, which we call an ethyl group. And it has CH2CH2CH3, which we call a propyl. And I'll write those names down for you. So this is CH2CH3 that is attached, which we call an ethyl group. This is CH3 attached, which I call a methyl group. This is your hydrogen. And this is a CH2CH3 group, which is called propyl. So these 2 molecules are enantiomers. They are mirror images of one another. They cannot be rotated to be the same molecule. Not with the angles of the molecule itself. With the tetrahedral angle of that molecule, it will never rotate to match it. So this comes in this idea of a mirror plane as well. If a molecule possesses a mirror plane, it cannot be chiral. Again, these are easier to see if you're actually holding onto a model. But if you remember what the way these models look, sorry, I'm trying to draw straight and it's just clearly not working. This is in the line of the board, and this is in the line of the board, which means theoretically I could cut a mirror that cuts through the line of the board and through the molecule here. This is going to give me that mirror image. So I'm cutting through the hydrogen, through the methyl group, and through these chlorines to go in the plane of the board. And it's giving me these two on either side of the compound. It is a mirror plane within the molecule. Because again, this is going backwards. This is going backwards. This is coming out at me. So if I cut a plane through the board, it cuts right through these two, and I've got a mirror plane, and it is not chiral. Same thing here. These may be mirror images, but they can also be rotated to be the same molecule. I can see here the mirror image, the mirror image, the mirror plane, the mirror plane, the mirror plane. They are not chiral. Your chiral molecules do not have a mirror plane. One way that we can tell that they're chiral, well, we can react them with something that's chiral, or we can measure their optical activity. A pair of enantiomers, meaning the compounds that are mirror images of one another, have all the same physical properties except one: the direction that they rotate the plane of polarized light. So we take a sample, we put it through what we call a polarimeter, which measures the amount of light that's transferred or that's rotated based on the sample. So you see you got your light source, your normal light, a polarizer, that's the instrument it's going through. You got your plain polarized light, and then, some kind of detector to it. It's analyzing, and then you view it, but it's going to rotate the light. So let's say I've got a sample, and this is our 0, point, okay? Our enantiomer may rotate it so it looks like this. But its counterpart, the other half of that enantiomer, is going to rotate it the other direction. So the direction in which they rotate the plane of polarized light, they rotate it opposite of each other. They rotate the same amount, so pretend those triangles are drawn the same amount. They rotate the same amount, but in opposite directions. So if one rotates it 1 inch this way, the other one's going to rotate it 1 inch this way. An equal molar amount, 1-to-1 mixture of the pair of enantiomers is called a racemic mixture. The rotations of each enantiomer cancel each other out, so there's no net rotation to the system. So which compounds can exhibit optical activity? If I ask you a question like this, optical activity means enantiomers. So I know I'm looking for something that has 4 different groups attached to the carbon atom. This carbon is out. It's got 2 hydrogens attached. This carbon is out. It's got 3 hydrogens attached. Let's see. This carbon is out. It's got 2 hydrogens attached. This carbon's out. It's got 2 hydrogens attached. This carbon's out. It's got 2 chlorines. This carbon's out. It's got 2 hydrogens. This carbon, however, has a Cl group, an H, an F, and a CH3. This exhibits optical activity because it has 4 different groups attached. Again, the carbon it's attached to is then attached to 3 different hydrogens. That is different than anything else attached here. It's not directly attached to those hydrogens, attached to the carbon first. So this compound will exhibit optical activity. Geometric isomers. Rotation around the double bond is highly restricted. Remember, that comes back to the pi bonds. We learned about this when we talked about valence bond theory. If I've got a pi bond between 2 carbon atoms, the first pi bond is above and below that internuclear axis. If I had a second pi bond, it would be in front of and behind that internuclear axis. So the double bonds prevent the molecule from freely rotating. It literally locks the structure in place so it cannot rotate around this bond specifically. If it was a single bond, if all these double bond and triple bond pieces were not here, this would have free rotation. But because of the double bond, it doesn't have that free rotation anymore. So different molecules exist due to difference in spatial orientation about the double bond. And we call these cis and trans isomers. Cis are groups that are attached to the same side of the double bond, whereas trans are groups that attach to the opposite sides of the double bond. So we can see here 1-chloryldiethane. It has free rotation around that bond. it can flip between these. These are the exact same molecule. But if I had 1,2-dichloroethene, ethene means, ene means double bond, means you've got a double bond present. I don't have free rotation. This cannot rotate. This cannot rotate. The entire molecule could flip upside down, but that itself cannot rotate. So notice here I've got the chlorines on the same side, same as cis. Here I've got the chlorines on the opposite sides, cis is trans. Now notice I mean opposite sides across that double bond. I do not mean that I have, sorry, one second. I do not mean that I'm putting both the chlorines on one carbon. That is a different molecule, okay? Notice it is named here 1,2. It is telling me where the chlorines are attached. This molecule would be 1,1-dichloro. Ethene, which is a different molecule, okay? So when I say switching, I mean across the double bond, not on the same molecule. But notice the densities here are different. So I've got 1.284 for the first one and 1.257 for the second. So the second compound is a lower density. Melting point of the first one is -80, whereas the second is -50. Boiling point of the first one is 60, whereas the second one boils at 47. So I see differences just there as well. Their physical properties will be different and their chemistry will be different. So is there a geometric isomer? Arrange the molecule with a central double bond and examine the surrounding groups. Would there be a difference if the groups on one side of the double bond were switched? Meaning if I switch these two around, would anything change? If I switch just these two around, would anything change? No, it wouldn't. It would look the same. This does not have a cis or trans to it. It's just a compound. If I flip these two around, it's still going to look the exact same. Okay? Even if I flipped these two around, I could still flip the molecule back over and it would look the exact same. Let's look at a couple others and see if we can figure out which ones would do it. Which would it could exhibit. So let's see if we can recognize the geometric isomerism itself. Let's try each one of these molecules and see, are any of them cis or trans, or are they just a molecule and they don't have a geometric isomer? First up, remember, hydrogens can only have one bond. So the hydrogen is bonded to this carbon. Here, the hydrogen is bonded to the carbon, and the CH3 group is bonded to this carbon. Okay? The carbon is the one that's going to double bond to itself. Just the way it's written can be a little confusing for students. Hydrogens can never have more than one bond. Don't give it to them. Hydrogen, 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 CH3. I'm going to flip the molecules on one side only. So let's just pick this side just because I can. Doesn't really matter. Leaving the other side the same. These are, in fact, the same molecule. It can be a little hard to see it, but if I was to flip this molecule upside down, it's a mirror image, but it's also the same structure. So it made no difference when I flipped it that I flipped the signs on, or sides, that I flipped these two groups around. It's the same exact molecule. Let's look at letter B. Got a CH3 on the carbon, an H on the carbon, an H on the carbon, and a CH3 on the carbon. So carbon, double bonded to carbon, an H, and a CH3. Some students will ask me why I sometimes write it like this instead of, it's a preference thing. This is just emphasizing that the carbon is bonded to the carbon, not the hydrogens, okay? You don't have to do it, it's just a preference thing. The other side, let's see, I've got a hydrogen and a CH3. So if I switch just these two groups, will it be the same compound? Now the CH3 is going to go on top, hydrogen on the bottom, leaving the other side of the molecule the same. I see that these are in fact not the same. These are geometric isomers. Here, my methyl groups are opposite of one another, so this is known as trans. Here, my methyl groups are on the same side. Notice I'm talking about methyl, not hydrogen. Hydrogen does not get a priority here, which is called cis. So, my answer is B. Let's just make sure that none of the others qualify. C, Cl2, and Cf2. If I switch these two groups, we can already look at it. It's going to look the exact same. So, no. And CHCl, CFF. Some students may say, but what if I switch the two that are different instead? Maybe that will do it. You can try it, but what you're going to find is it's not going to matter. These molecules can be rotated to match each other. It's basically like just flipping this molecule upside down to get to the same molecule. So it is, in fact, B as the answer here.